All right, we are going to start this video let's start with example 3 actually, and not example 2. Okay, so if we start with example 3, supposing that you don't remember or you don't know that this is a graph of oh goodness, what just happened? Okay, supposing that you don't know that this is the graph of a parabola, you would, in the initial stages of trying to understand how to do this, you would probably plot some points. So let's say you make a little XY chart and you pick -2, -1, 1 and 2. Let's say you forget to pick 0. So you get, what, 2, 2, you get -1, -1. And if you plot these 4 points, sorry, it's very messy, but I'm trying to get through this quickly. So if you plot these 4 points, if you don't know that this graph is a parabola, of course parabolas look something like that. If you don't know that this graph is going to do that, then, what's to prevent you from filling in these 4 points with a V? Or what's to prevent from you drawing one of these things, one of these weird curvy type graphs. So the point of just talking about this is that recognizing what type of function you're dealing with as soon as you see an equation is often a very helpful and useful way to approach graphing. And we know that that's true, when you look at example 2, which was y equals, 7 minus 3x or something like that. Yeah. So if you know that this is a linear equation, then you know that all you need is the y-intercept and the slope. And then you could just get those 2 points and then draw the line, because you know this is a linear equation. If you didn't know it was a linear equation that was going to make a line visually, then you would have to plot a whole bunch of points until you get enough proof to yourself that this is a linear equation. So again, bottom line is recognition of the type of function you're dealing with is a very helpful tool to graphing. Okay. Another helpful way to sketch a graph, particularly when the graphs start to get a little bit weird and uncommon, is finding intercepts. So intercepts, of course, refer to the points where a graph would cross an axis, x or y axis. So the basic idea here is if you want to find y-intercepts, you set x to 0 and solve for y. And if you want to find x-intercepts, you set y to 0 and solve for x. Okay, now why exactly does this procedure or this rule for finding intercepts work? Well, it's real simple. If you think about, let's say, the x-axis, right? No matter what point you pick on the x-axis, what do all of those points have in common? Well, every one of those points has a y-coordinate or y value of 0. So therefore, if you want to know where a graph touches the x-axis, you would want to know where the y is 0 and what the corresponding x would be, right? And similarly, if you want the y-intercept, all points on the y-axis have an x-coordinate of 0, which therefore means that if you want to find out where a graph crosses the y-axis, you would first let x equal 0 and then figure out what the corresponding y value would be. Okay, so you could look at example 4, it gives you an example of how to find intercepts, but that's the conceptual behind that. Okay, let's move on to symmetry. So in symmetry, there are 3 basic types of symmetry, and I'm going to import some photos here, so let me pause it. Okay, so the 3 types of symmetry are symmetry about the x-axis, symmetry about the y-axis, and symmetry about the origin. Okay, so x-axis symmetry, let's just take a look at what happens when you have x-axis symmetry. So let's say you have a graph that looks like this. That's not a very good drawing. That's a little bit better. Okay, so what happens when you have symmetry about the x-axis is that it implies that if there is a point that exists called xy, that there has to be another point opposite the x-axis that also exists. So opposite the x-axis means you're going down instead of up, so the coordinates here would be the same x, but the opposite y. So the way that that's represented in terms of the graphical test is that whenever xy is on the graph, x negative y is also on the graph, as you can see in the drawing that I put below. Okay. Now similarly, you could do the same thing for if there's y-axis symmetry. And then origin symmetry refers to, well, let me do the y-axis symmetry case first real quick. I'm sorry about that. I wanted black. Okay, black. Okay, still getting used to this tool here. All right, so if you have y-axis symmetry, let's say it's a V, then that implies that if you have a point, let's call it xy, that there is another point across the y-axis that also exists. So this would have the opposite x value, but the same y value. Okay, so if xy exists, negative xy also exists. Okay, and then the last case is if you have origin symmetry. So origin symmetry is when for every xy that exists, and you can see it right here, negative x, negative y also exists. And the way that I would describe kind of visually what that would look like is if you imagine that the origin is a knob, okay? So imagine that there's like a little knob right there in the origin, that if you have a point here and then you twist that knob 180 degrees so that this point rotates around 180 degrees, you would have another point there. Okay, so that's origin symmetry. A classic example of that would be like a cubic function, right? So let's take a look at a cubic function and see how it has origin symmetry. So a cubic function looks something like this. And so you could see that for every point xy, if you rotate it around this knob 180 degrees, you will find another point with the opposite x coordinate and the opposite y coordinate. So that is origin symmetry. Okay. So hopefully that gives you a little bit of an understanding of what are the characteristics of a graph when it has that type of symmetry. Okay, now as far as when you have a function or an equation and you want to test to see if it has any type of symmetry, that's when you use your algebraic tests for symmetry. Okay, so let's do an example of that to give you a little bit of practice. Okay, let's look at, example 6, ought to do the trick. So let's say I have x minus y squared equals 1. Now, what type of symmetry will this graph have, if any? Okay, a graph does not necessarily have to have symmetry, but does this one. So let's run the tests. So the first test is, could we replace, well, I guess the first test, could we replace y with negative y? And if we do, what happens? So if we replace y with negative y in this equation, well, negative y to the second power is positive y to the second power. So you could see that we ended up with the exact same equation that we started with. So that is an indicator, therefore, that this graph has, x-axis symmetry. X-axis symmetry. Okay, now you could run the other test as well. So if we start with x minus y squared equals 1, and this time if we replace x with negative x, you can see right away that there's nothing you could do to make this equation the same as that. They're totally different equations. So that means, therefore, there is no y-axis symmetry. And in order to have origin symmetry, it would have to have both. So what I mean by that is if you start with the original equation, if you replace both x with negative x and y with negative y, oh, that's not a y, that's a y. What happens is you end up with this equation, which again is not the equivalent as that. So therefore, there's no origin symmetry. Okay, so that's how you run the tests. So once you know that it has x-axis symmetry, that's good, because then for every point that you get, you're actually going to get a second point across the x-axis. And so this video is getting kind of long, so I'll just have you go ahead and look at example 6 to see how the rest of this plays out in terms of the graph. But it's just point plotting and then understanding that there's symmetry to that point plotting. Okay, as far as circles are concerned, the characteristic of a circle is that a circle, by definition, is the set of all points. So not only this one, but also this one, and 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 every single other point that has the same distance to the center point. So this distance would also be r, this distance would also be r, this one would also be r. All of them is r, right? So that means, that would imply that that distance is a constant, which is called the radius. So using the distance formula, we know that the radius is the square root of x minus h squared plus y minus k squared. That's the distance formula from point center, which is hk, to any point on the circle, which we could generalize as x and y. So this is an equation for the radius. And then if you square both sides of this equation, you get r squared equals x minus h squared plus y minus k squared. And so this is what we call the standard form equation of a circle. And we'll just flip the sides. So we'll just switch sides here. And that's how they get the equation of a circle. Okay? All right, so let's just look at a basic example of this, and we will be done with this too long video. Sorry about this. Okay, so let's say you have a point 3,4 on a circle, and it has a center at -1, 2. Okay, now you visual people, if you want to draw this, you can draw it. So -1, 2 is your center, and then 1, 2, 3, 1, 2, 3, 4 is a point on the circle. So that means that that's your radius. So your circle is going to look something like that. Okay, not a great picture, but you get the idea. Okay, and this is -1, 2. Okay, so the first thing you need to do is find out what the radius is, right? So the radius, using the distance formula, is, we'll go -1 minus 3 squared plus 2 minus 4 squared. So that would be -4 squared, which is 16. This would be -2 squared, which is 4. So the radius is the square root of 20. So now you have all the information you need, right? You've got the radius. That is not pretty. Never mind that. Let's forget the highlighter feature. So you've got a radius that's 20, and you have the center, which is -1, 2. So all you got to do is take your equation of a circle, right? Remember, equation of a circle is this. And replace h, k, and r into the equation. So h is -1, k is 2, r is radical 20. So we got x minus that squared plus y minus that squared equals that squared. Simplify it, so you got x plus 1 squared plus y minus 2 squared equals 20. And that is the equation of the circle. Again, my apologies for the length of the video, 14 minutes. Hope you have a nice weekend. Bye-bye.